Okay, let's try another problem. And this problem is to find the volume of the voids, the volume of the solids, the weight of the solids, and weight of the water, given that we have the volume is 50,000 cubic feet, the water content is 0.14, the void ratio is 0.48, and the specific gravity of the solids is 2.2. So you should pause the video here and solve this problem. All right, I am assuming that you have solved this problem, and now I'm going to give the answer. Well, first of all, let's look at a couple things when we solve this. First is note that we have been given the volume. If we've been given a volume, we cannot make any assumptions about weight or volume. So we have to work with this data, no assumptions allowed. Second thing we notice is that I've been given the volume and the void ratio. Well, what should trigger into your mind? If I'm given both the void ratio and the volume, then I have two equations, two unknowns. So let's start there. That's the obvious thing to start with when you're working a problem like this. Start with the obvious. And so we have the volume, 50,000. It's equal to the volume of the voids plus the volume of the solids. The void ratio of 0.48 is the volume of the voids over the volume of the solids. That means I have two equations, two unknowns. I can solve for the volume of the voids and volume of the solids. So you can work with this equation first. I get that. I take this 0.48 Vs, and where do I put it? I put it right there. So that means that I get a new equation. I solve that equation for Vs. I get Vs is equal to 33,783 cubic feet. And then I simply subtract that number from the 50,000 and I get the volume of the voids. Okay, so now I have both the volume of the voids and the volume of the solids. Now since I know the volume of the solids, I can get the weight of the solids if I know the density of the solids. Because remember, density is the thing that's going to bridge us between weights and volumes. In other words, here I've solved the volumes, I need to get the weights. So if I have some density information, that is going to help me out. Well, do I have the density of the solids? Well, I do. Why? Because I have the specific gravity of the solids that's given. So I can go from volume of the solids to weight of the solids because I know the density of the solids. So density of solids is weight of the solids over the volume of the solids, which is G sub S times gamma W. And so my weight of the solids is going to be G sub S gamma W times Vs. Very straightforward. Plug in that. I get that's the weight of the solids. And then how can I get the weight of the water? Well, I know that the water content is weight of the water over weight of the solids. And I'm given the water content as being 0.14. So I can, again, simply plug that in. I get that. And then I solve for the weight of the water. There's my weight of the water. And I have solved for everything that we need. All right, the next problem that I'm going to describe is a classic problem that is asked on almost all the fundamental of engineering exams. It's the classic borrow pit problem. What do I mean by the borrow pit? Is that generally we want to create a fill of some sort, and where does the dirt come from? It comes from a borrow pit. So there's my borrow pit. There's my borrow site right there. And my goal is to take the soil from the borrow pit and create the fill. And frequently we have some specifications for the fill. In other words, we need a particular volume of the fill. the question becomes, what is the borosite volume? What borosite volume do I need to create that? Well, it's not going to be the same as the volume of the fill. Why? Because when I put down the fill, I always compact it. The fill, we never put down fill without compacting it. It's not a good idea because we need to get specific properties of that soil, and if you just take and dump that soil, it's very loose, it just doesn't work out. So we compact that fill, which means that usually the soil at the borrow site is less dense than the density of the soil at the fill site. And so that means that usually the borrow pit volume is going to be greater than the fill volume because the soil is less dense at the borrow site. Generally, it's a bigger volume than the fill. Okay, so I'm going to give a problem, and I'm going to say that we have an initial condition, which is at the borrow site, and we have a final condition, which is at the fill site. And I'm just going to give some information. I'm going to say that the void ratio in the initial condition, I'm calling it E sub I, is 0.95, and the void ratio in the final condition is 0.65. So notice the void ratio has gone down. What does void ratio mean? You can think of it to a certain extent as volume of the voids. So in other words, the void volume has gone down, and that makes the soil more dense. So it's more dense at the fill site. And we have our final fill volume of 5,000 cubic feet. In other words, the volume of that fill that I'm showing there is 5,000 cubic feet. Given these other properties, I want to know what is the volume needed at the borrow site. We can draw a little sketch of this, and sometimes it's very helpful to get an idea what's going on to do this because we have an initial and final. So this is different from any of the problems that we've done previously. In the previous problems, we didn't have two different conditions. We just had one. I told you these are the properties of the soil and give me some other properties of that soil. Now I'm adding a complication. I have an initial condition, and then I'm doing something to the soil. I have a final condition, and I have to essentially correlate the initial and final conditions to help me solve this problem. So if I draw this little sketch, so I'm indicating air, water, solids. Air, water, solids. Now, what is true between the initial and final conditions? Well, the only thing that we know is constant is the volume of the solids and the weight of the solids, of course, but I'm just sort of drawing this picture. So if you're drawing a picture like this and you want to get it right, you should, or to help, in other words, you're trying to help yourself visualize what's going on. And so when I draw this, I want to draw this initial volume of the solids to be the same as the volume of the solids final, because we are not going to add or subtract solids. So they are the same. On the other hand, notice that the water is different. Why? Because frequently we add water when we compact the soil. So in other words, as we're going like this, we add water. And so that when I draw this picture, I don't want to show the water being the same. They're different. And then when we compact it, what do we see? Well, when we compact it, well, the air is reduced. So to just get so it's helpful to draw something like this to give yourself a feel for what's going on in these initial and final problems. So let's look how we can lay out the solution the easiest way. We're going to have an initial, final, and then a linkage between the initial and final. That's going to if you make those three columns and put information in each of these columns, then that's going to help you think this problem through. And what do I see in this linkage? I have the initial condition, final condition. Well, what's equal and what's not equal? And what we see is that the way the solids in initial and final are the same. Now, what we list here are all my weights and volumes. What are my weights and volumes? So I have two weights, the weight of the solids and weight of the water, and I have three volumes. Volume of solids, volume of water, volume of voids. So I want to list all of those. So the way to do this is listed. Weight of the solids, weight of the water, volume of solids, volume of the water, volume of the voids. And then I put the same thing over here, and then I just decide, do I have an equal sign or do I have a not equal sign? So to get this started, there are different ways to do this. And I just put either an equal sign or not equal sign. Well, what do I know? Weight of the solids is equal before and after. Volume of the solids is equal before and after. But the weight of the water, not equal. The volume of the water, not equal. Volume of the voids, not equal. And this picture has helped guide me to be able to write that out. Now, once I've thought this, a lot of the purpose of this is to think this through, because these problems can be a little bit cryptic and you have to sort of think them through, and that'll help guide you through this. So I list what I know initially, and I list what I know in the final condition as well. So this is just the given information. So my given information I've simply translated and put them in this column, and now I'm going to look for what I want to start solving some things. And well, one of the first things I see is what? I have void ratio and volume. What do I know there? Two equations, two unknowns. When I've been given that, I have two equations, two unknowns. I write out the equation. This is void ratio, 0.65. My volume of voids plus the volume of the solids. What do I have? Two equations, two unknowns. I can solve for those. I get this for the volume of the voids and that for the volume of the solids. Now, what do I know? Since I've gone through this exercise here, I know that the volume of the solids, initial and final, is the same. So what can I do with that volume of the solids? I can put it over here in this column. I now know my volume of the solids to use for the initial condition. And here I've been given that the void ratio is 0.95, so I write that out, volume of voids over volume of solids. I know the volume of the solids, so I can put that in, and I get the volume of the voids initially is 2880. And what does that mean for me? Well, if I take the volume of the voids and the volume of the solids, add them together, I get the total volume, and I get the total volume of 5910. So the volume of the volume of the soil at the borrow site that I need to take away is 5910, and I end up with 5,000 cubic feet in my fill. Let's try another one. It says that a wet soil, okay, so the soil is not dry, that weighs 200 kilonewtons. Okay, now remember that weight of 200 kilonewtons is what? It includes water and solids together because the soil is wet. It has a water content of 22%. Okay, so I know the water content. The soil is dried out completely without changing volume. And then it has a unit weight of 16 kilonewtons per cubic meter. Okay, it's dried. So what does that tell me? The dried unit weight, dry density, 16 kilonewtons per cubic meter. That means the dry density is 16 kilonewtons per cubic meter. I want to know what was the original volume. Okay, so what are we doing here? Let's draw a little sketch. Again, I have an initial condition, I have a final condition. Initial condition is before we dried it out and after we dried it out. Now, so I have my box here, and in my box I have air, water, and solids. But for the final condition, it's dried out. Dried out completely. So that means, and I've done it without changing volume. So if I want to draw a nice picture that's going to help me with this problem, the way to do it is that I'm drawing this box is the same size as this box. I haven't added any solids, so what do I see? I see that, this, if I want to draw this out, that box and that box are the same. But what has happened? I've dried it out. So what's happened is now the water is missing. So all I have is air and solids over here. Okay, so that gives me an indication of what we've done here. I've gone from this condition with the water, same volume, no water, just air. And I know I've been given that the weight is 200 kilonewtons and the water content is that, and I've been given that density. Again, I have been given a weight, so I cannot assume a weight or a volume of any sort. All right, so again, let's do the linkage here. What do I see? I have initial and final. And again, I list my weights and volumes. Now I have weight of the solids, weight of the water. Volume of the solids, volume of the water. Then volume of the voids. Now I've got total volume as well. So I've listed my weights and volumes, and then I just have to decide, are they equal or not equal? What do I see? The weight of the solids, same before and after. Weight of the water, clearly not, because I've lost all my water. Volume of the solids, the same. Volume of the water, not the same. How about volume of the voids? Volume of the voids is the same, right? Because there are my voids, there's my voids. So the voids is the same. And the total volume is also the same. Why do we know that? Because we drew the total box is the same. Okay, so the whole purpose of drawing the picture and drawing this linkage out is to get you to think about this problem and to get an image in your mind of what this is about, and then it's going to help you solve this problem. All right, so now we look for, well, let's look at what we know. I know capital W and small w. What does that mean? That means I have two equations and two unknowns, if you know the shortcuts that I've taught you. So I've got weight of the water plus the weight of the solids is 200, weight of the water over the weight of the solids is 0.22, two equations, two unknowns. I'm not going to go through it again. I get that weight of the solids, I get that weight of the water. Now, what do I know about the before and after? Well, I know that the weight of the solids is the same before and after, so I take the weight of the solids, I put it there. And then what else do I know? I know that my density is 16 kilonewtons per cubic meter, and that is gamma D because it's dry, which is the weight of the gamma D is weight of the solids over the volume. And so it becomes a simple problem there. I simply plug in, I've got 16 for my gamma, I've got 164 for my WS. I simply solve then for the volume, and I get 10.24 cubic meters. That's that problem. Okay, let's read through this one. Now, it says a wet soil with a unit weight of 112 and a degree of saturation of 28%. We start there. We change the volume, okay, and have a new void ratio of 1.86. What is the new degree of saturation, water content, and density? Use GS equals 2.5. Now remember, whenever I've given a G sub S, that means that you can go easily from the weight of the solids to the volume of the solids, or from the volume of the solids to the weight of the solids. It's very straightforward because you know you have the G sub S. That means you have the density of the solids. So that's what should key in your mind as you solve this problem. So in the solution, I'm going to get you started with the solution here. We have the initial condition, we have the final condition. Well, what have we done? We have to we note in this, I didn't read the last sentence here, which is we do not add or subtract any solids or water, but we change the volume. Okay, so when I draw this figure, well, I'm going to show the volume getting bigger. I don't know whether it gets bigger or smaller, but just to get it started. Notice those boxes are not the same size. The one on the right I've shown bigger than the other. Why? Because we're changing the volume. But the water is the same. The solids is the same. So the only thing we're changing is the air. So when I make my little table for the linkage and my initial and final, I have what? Again, weight of the solids, weight of the water, volume of the solids, volume of the water, volume of the voids, total volume. Those are my weights and volumes that I write there. And then I decide are they the same or different between initial and final. Well, the weight of the solids is the same. Weight of the water is the same. Volume of the solids is the same. Volume of water is the same. But what do I know? The volume of the voids is not the same, and the total volume is not the same. So those are the linkages that I have. It's going to help you get through this problem. And now I list what we know initially and what we know final. So that's in the problem statement. So what I want you to do is pause the video here and work to solve this problem. Okay, I'm going to assume that you paused the video, and now I'm going to solve it. So, okay, in this particular case, I have my gamma, and I have an S, and I'm also given the G sub S. So I've given those three, and in this particular case, I can use one of the shortcut equations. So if I look at this shortcut equation, I have everything in that shortcut equation except the E. So I can solve for the E. So I just plug everything in. You can all do that. I solve for the E. There's my E. And then what do I have? I can use another shortcut equation. And in that particular shortcut equation, I have everything except the W. So let's solve for the W in that equation. So I just plug it in again and I solve for the W. There's my W. Okay, so when I look at this, now obviously this is my initial void rate. The void ratio changes. We already know that. Why? Because the volume of the voids changes. So it's obvious the void rate. So I cannot use this void ratio does not go over here. I can't do that because it's not the same void ratio. However, if I look at the water content, which is weight of the water or weight of the solids, what do I know? The weight of the water and the weight of the solids are the same before and after. That means that the water content is the same. So I can take this water content and put it in the new location here. And again, once I'm over here, I've been given the E, and I have been given the G sub S, and then now I have the water content, and I can solve for S. So I just simply plug it into that expression, and I solve for S. And then in the end, the last thing that I want to know is the gamma. So it's straightforward because now I can work with this other shortcut equation. I have all the values, I plug them in, and I get that number for my gamma. Okay, I'll stop there.